Now I'm going to discuss another method called the branch and bound method for pure and mixed integer program problem. For the details, I already wrote them there, or you can read the textbook. And here basically is that if we have three variables like x1, x2, x3, and for the LP problem, we already have the optimal solution by the method we know. And what we do is we work on each of the variable. If we want them to be integers, then we just separate them to be, okay, x, for example, x1 is between 1 to 3, then between 1 to 3. So in this one, we just choose the, okay, first we work on x1. x1 could be 1, x1 could be 2, x1 could be 3. Then once we get the result for each of them, and then because x2 is between 0 to 1, so because we need integers, so we say, okay, when we have this result, how about x2 equals 0, x2 equals 1, x for this branch we use that. So these circles, so that when we get the result, that we call it as a node, and that from the optimal solution, then connect for x1 equals 1, that is called a branch. And then we just separate work on them. Okay, so this is the basic what we call that, branch and bound method, right? And basically what we are going to talk, the method is called the Dawkins method, and basically we use only two variables to just two branches to check. Okay, and here for each node there will be two branches to check. If neither of the branches ends in a terminal node, then the method follows the most promising branch, and the other branch is called diagonal and must be examined before the algorithm terminates. So here, so when we say a node K is said to be terminal node if the set of solutions has been implicitly illuminated, or there are no feasible solutions satisfy the constraints imposed at the node. Okay, so here let's working on the just mention the Dawkins method. Here I already wrote the details, step 1, step 2, step 5. So here you can read them by yourself. And what I'm going to do in this video, I'm going to talk about the example we are working on it. Okay, so from the example you can easily to see what's going on there. Now let's see this example. This one actually back to the example 5.2. Okay, we already worked out it by cutting plane method. So here we have a minimization problem and we have a final tableau like this, right? Final tableau. So here what we do is we write the road in this way, so that I'll use the pen write down it. So this is the tree solution start as we call it a node 1. Node 1 is the solution for the final tableau. Z equals minus 15 over 4, and at x1 equals 5 over 4, and x2 equals 5 over 2. So you normally compare according to the steps. You could see that whenever we have the values for the basic variables. This one is a pure integer program, and we want x1, x2 both as integers, right? So here, the fractional part for x1 is 1 over 4. The fractional part for x2 is 1 over 2. So normally we start at at the largest fractional part. So here you could see that's 5/2. So in this way, we are going to make a branch of x2. How may we work out it is we make the branch is like this one, and x2 equals to 5/2. Then the largest integer less than 5/2 is 2, and the smallest integer greater than 5/2 is 3. So we simply just around that this number 5/2, we choose that two choice. And then the first branch is we work on x2 less than equal to 2. And the second one, we work on the condition x greater than equal to 3. So that one is the largest integer, which is less than equal to 5/2. And this one is the 3 is the smallest integer greater than equal to 5/2. Just two integers around 5/2. And then what we do is this one we just simply work if we start work on x2 less than 2. Okay, so for x less than 2, for x less than 2, that one we add a slack variable. It turns to x2 plus u1. We use another notation to denote a slack variable. Okay, we use u1 to denote this slack variable. x2 plus u1 equals 2. And that actually means we add a new constraint to the original LP problem. So this original LP problem actually was two constraints. Now we add x2 less than equal to 2. So we don't have to work it from the very beginning. We can bring x2 less than equal to 2 into the final tableau here. So final tableau here. Now, when we try to bring the final tableau here, you could see that x2 actually is a basic variable in this tableau, right? So x2 is a basic variable in this tableau. We may not bring this constraint directed into the tableau. We have to make that x2 to be 0. So in this way, we just write this constraint, follow it. We have x1, x2, s1, s2. So here, this constraint is 0, x1, 1 x2, 0 s1, 0 s2, and u1 constant 2. So this one we have, because we wanted to just x2 to disappear in the new constraint, right? So we use the second row, and that is 0, 1, 1/3, 1/6. But this row we don't have u1, so you keep that 0 here. We use that 0 to replace it. And then the constant is 5/2. Now we just want x2 disappeared in the new constraint. Then we get that 0, 0, negative, which is minus, right? So 0, 0 minus 1/3 minus 1/6, or negative 1/6, and then 1 minus 1/2. Now this is the new constraint, and we bring it into the final tableau, and that's what we got. Then we use dual simplex method to restore the feasibility, and that's the result we got. Z equals 13/4 at x1 equals 3/4, x2 equals 2. So when x2 less than equal to 2, and here you could see that we have, okay, just move it a little bit. So we have z equals minus 13/4 at x1 equals 1/3, 3/4, x2 equals 2. Now we just this one, we just let it dangling here. We will deal with it later. Now we work out this one. This one, we have the condition just so we want x2. Okay, here should be x2. I missed the 2 here. So here is x2. So we want x2 greater than equal to 3. Now we just bring the condition into it that x2 greater than 3, then we add another slack variable. We add that x2 minus u2 equals 3, right? We have to minus make the equation. So this turns to, we have to keep that u2 to be the basic variable, right, with the coefficient 1. So that turns to, it is minus x2 plus u2 equals minus 3. But the same as x2 is basic variable in the final tableau. So we just bring the second row into here and to make that x2 disappears. Now the new constraint here becomes that 0, 0, 1 third, 1 sixth, 1 minus 1 half. So now we bring the new constraint into the final tableau. You could see what we got. Here we have this tableau. What we find out as 0, that's the final tableau, and then add the new constraint into here, third row. And the new constraint, what we bring it is 0, 0, 1 over 3, 1 over 6, 1, minus 1 over 2. And here you could see in optimal case, but the solution is infeasible. And according to dual simplex method, we have to work, we only can work on those aij with negative value. Here we found all the entries on the third row, and they are non-negative. So in this way, we cannot go any further. So that means if we let x2 departing and there's no entering variable there, that actually means there's no feasible solution. So in this way, we could say that, okay, now if we ask x2 greater than equal to 3, there's no feasible solution there. So this is a terminal node. We cannot go any further. So x2 in this problem, x2 cannot be greater than equal to 3. Now, what we are going to do is we just, this node 2, right? Node 2 is dangling there, right? So now we back to the node 2. Node 2, we have x2 as an integer, but x1 is 3 over 4, the only one we want it to be integer, right? So the integer around that 3 over 4, the largest one less than 3 over 4 is 0, and greater than the smallest integer greater than 3 over 4 is 1. So we just use another 2 branch to work on it. That is, we consider that x1 less than equal to 0, and another one is x1 greater than equal to 1. So one, we are going to continue to work on it, but here you notice that when we work on it, we need to add this constraint into the final tableau. When we work out this constraint, we bring it to the final tableau of the node 2. Okay, not the final tableau of the simplex method, because we have this step already, right? x2 less than 0. So we will bring the step into it. Now, so now we have the condition x1 less than equal to 0. So in this way, actually, because we need all the integers to be non-negative, right? So here, actually, if we get the result, x1 should be 0. So here we add that x1 plus u3 equal to 0. Okay, it's under the node 2. So here, because x1 is basic variable in that tableau, T22, right? And here each step I make a note for those tableaus. So this is for the note 4, I have T41, T42. If you go up, you could see that I worked on this. This tableau is T21, that's T22. Okay. Now, in the T22, that x1 is the basic variable, so we bring that the row where x1 is a basic variable, and then we remove that x1 from the new constraint, and then we bring it into the tableau. And when we bring it into the tableau, actually we got we normally use that dual simplex method to install the feasibility. And when we work on that, you could see what's the result. So here we have that x1 equals 0, but the problem is that x2 becomes 5/4 is not integer anymore, right? But we do have an optimal solution is z equals minus 5/2 at x1 equals 0, x2 equals 5/4. And then we just net it down in here, right? And we discuss the other branch that x1 greater than equal to 1. For x1 greater than equal to 1, let's see that we do the same thing, that we settle another new variable, x1 minus u4 equals 1. And then minus x1 plus u4 equals minus 1. Here notice that on the note 2, we already have a slack variable u1, right? So we have to include it. Now we just bring it, okay, with that first row of the T22. Note that this one is not based on this. This one is under this one, right? Node 2. So when we work on it, we just bring the final tableau of node 2, T22. Okay. So in this way, when we bring it into that, the T22 gives us that we can remove that x1 from the new constraint. Now we bring it into the T22. Okay, we bring it because we get this one from T22. So in this way, we bring it back to the T22 and we get this tableau. We call it as T51 because this is node 5, right? T51 and T51, it is in optimal case, but U4 equals minus 1/4. And now we just restore the feasibility by dual simplex method, and we could find out that this is the result. And this one actually is what we got from that cutting plane method. You could see z equals minus 3, x1 equals 1, x2 equals 2. So here it's not done yet. So we write it down yet. It's not done yet because this one is hanging there. This one we already got the optimal solution for that integers, right? And in this way, this is a terminal node. Okay. So for this one, actually, we have to go further to discuss x equals 2 and equals 5/4. So in this way, we know that it is greater than equal to 1, less than equal to 2. So now we consider x2 less than equal to 1 and x2 greater than equal to 1. So these two branch, and we can do the same thing, work out it. And what we got is that z equals minus 9/4 at x1 equals 1/4, x2 equals 1. But you notice that if we work out this one, you could see x1 is 1/4, but here we have x1 less than equal to 0. So x1 has to be this result. Actually, we don't want it, right? And for x2 greater than 2, that's okay. But we have no feasible solution. We do the same thing and no feasible solution. That's what we work on at. Okay, x1, x2 less than 1, we introduce a new new snack variable and then solve it, and that's the reason we got this result, which is not accepted because x1 should be less than equal to 0. We have the constraint there. So x1 actually in the in the branch 6 we should have x1 equals 0, right? And then is for the x greater than. Okay, so you may make a copy. That for x2, we bring it into that. You could see there is on the left of the row, the new constraint here. You could see there's none of them is negative. So in this way, if you bring this constraint into the top row of T4. For T42, and you could see that we can't reinstall the feasibility. So this one, no feasible solution. Actually, we do not need to work on the node 6 and node 7. Why? Because here you could see that when we calculate each step, this one z value is minus 15 over 4, and this one z value is minus 13 over 4, which is what? Greater than this one. And when we work on this z equals minus 5 over 2, which is less than which is greater than negative 13 over 4. And the node 5, we get the result z equals minus 3, which is what? Less than it. But you can compare the optimal solutions at node 4 and node 5. You could see node 4 at this stage that z equals minus 5 over 2 is already greater than z equals minus 3, because this is a minimization problem. And if we do further work and branch, and we will get the z value bigger than the z value at the fourth load. So there's no reason we want to go further. So here I wrote what I want to say, that is, we don't have to calculate nodes 6 and 7. Comparing node 5 and node 4 and node 5, the value of the objective function in node 5 is less than the one in node 4. Any further branching on the node 4 will not decrease in the value of the objective function, as you may see in the node 6 and 7. So in this way, the optimal solution is the 5 on the node 5. That is the final the optimal solution for this example 5.2, which is the same as we worked with the cutting plane method, right? Now we are going to talk another method, another example. That's example 5.4. Here we have an LP problem maximizes z equals x1 plus x2, and subjected to these two constraints. Now we want to find the optimal solution for x1, x2 to be integers greater than or equal to 0. Now first we use a simplex method to find the optimal solution for x1, x2 greater than or equal to 0, and then note that x1 and x2 both are non-integers, right? Non-integers. Okay, so here the optimal solution is z equals 29 over 6 at x1 equals 3 over 2 and 10, x2 equals 10 over 3. And the way, if we want to give the solution for this example, and actually we just simply use the tree structure, and that's the solution for this one. Okay, so here when we have the first by simplex method, we have z equals 29 over 6 at x1 equals 3 over 2, x2 equals 10 over 3. Then, as you could see that the fractional part of x1 is 1 over 2, fractional part of x2 is 1 over 3. So of course we start our branches on x1. So the x for 3 over 2, right? So here the left branch is we consider x1 less than equal to 1. And the right branch is we are working on x1 greater than equal to 2. So the first one, when we add the new constraint into the final tableau of the Note 1, and then we use the dual simplex method. We can work out it to get z equals 10 over 3 at x1 equals 1, x2 equals 7 over 3. Then we just net it dangling here. We work on that x1 greater than equal to 2. When we plug in this new constraint into the final tableau in the row 1, and we get that z equals 4109 at x1 equals 2 and x2 equals 2309. And now what we do is compare these two values. Z equals 10 over 3, z equals 41 over 9. This one is what? Greater than equal to 4, right? This one is greater than 3, less than 4. So what we would do is, because the original LP problem is maximization, so we just net that note 2 dangling there. We are working on note 3 because this objective function has the larger value, right? So we work on this one. That's why this is node 3. Now we work on node 2. So with this one, x1 is integer, but x2 is 23 over 9. So the 23 over 9 is between 2 and 3, right? So here the left branch is x2 less than equal to 2, and the right branch is x2 greater than equal to 3. So now we work on the note 4 when we add the constraint into the final tableau of note 3. And that we got z equals 61 over 14 at x1 equals 33 over 14. Well, x2 equals 2. Right? Now we have x2 become integer, but x1 is not integer. Okay, but we just leave it here, just let it stay there. Okay, dangling there. We work on that x2 greater than 3. When we bring this new constraint into the final tableau of note 3, and we found that there's no feasible solutions, so we just leave it there. Okay, now when we have this one, we have to continue to work on it. Note 4, we have to continue work on it. So here, what we do is we net it dangling there, okay, to be a dangling note, and we back to note 2. And we work on, for the note 2, you could see that x1 is a integer, x2 equals 7 over 3. And then for x equals 7 over 3, that is between 2 and 3, right? So the left branch is x2 less than equal to 2. The right branch is x2 greater than equal to 3. And then when we solve this one, we got the optimal solution. Bring it, note here, be careful, because this new constraint, we need to bring it into note 2 final tableau, right? So here, when we bring it into, we solved it by dual simplex method. We found the optimal solution is z equals 3 at x1 equals 1, x2 equals 2. And so this one is a terminal root. And then we back to it to work on x2 greater than equal to 3. We found that there's no feasible solutions. So far, on this stage, the third stage, we have node 6 give optimal solution z equals 3 at x1 equals 1, x2 equals 2. This is integer result, right? And node 4 and node 5, no feasible solution. So we have node 4 dangling there. So we have which one, x1 is still non-integer. So we have to continue to work on that. Now here x1 equals 33 over 14 is between 2 and 3. So we net x1 less than equal to 2 and x1 greater than equal to 2. And then what we got is this one. Okay, the optimal solution z equals 4 at x1 equals 2, x2 equals 2. And z equals 4 at x1 equals 3, x2 equals 1. So you could see here, these are terminal nodes, so we don't have to go any further. This gives us optimal solutions z equals 4. But at different points, this value for objective function could be reached. Okay, so z equals 4. And here we also have 1. Then this one, z equals 3, is less than z equals 4. So in this way, the optimal solution is z equals 4 and at these 2 points. So in this way, we could say that this problem, we have multiple optimal solutions z equals 4 at these 2 points, 2, 2, and 3, 1. Do you say there's multiple optimal solutions on the line segment between 2, 2 and 3, 1? No, because here we want what? Integral result. And the points between them are not integers, right? So in this way, we have multiple optimal solutions at z equals 4 at these 2 points. Okay, this is the end for integer program problem.